Alright, good afternoon everybody. We are recording. Any questions? Questions on PA2 or lingering questions on PA1? Questions on hashes?
I have two questions on PA2 if you don't mind.
Go for it.
So on your sample executable, when you switch to Q mode, it prints head, tail. If there's nothing in there, it obviously doesn't print anything in there. If we have it to where it just switches, if it's empty and not print head, tail, and only prints head, tail if it actually has something in the queue.
No, I want to see head, tail even if it's empty.
Even if it's empty, okay.
Yeah.
And then you also have switching to stack and switching to queue, which always comes up if it's, even if you're already in stack and hit S. Is that, so you want us to, verify where we are in or which mode we're in basically?
Yeah, that's easiest to do. If you wanted to, check to see what mode you're already in, and if you're going to the same mode, not say anything, that would be kind of an extra feature, but let's not do that.
Okay.
And it also lets people know if they don't realize they're starting in stack mode, and they say stack and they're already there, it wouldn't say anything, and then they might be confused what mode they're in.
Oh, I guess that's true. You have to put like you're starting in stack
right,
mode and
right.
Like welcome. And we don't have to put a welcome message, you said, right?
That's correct. You can just print a prompt and just wait.
Okay. Okay. I think that's the end of.
Cool. Is anybody else having low volume from me?
Nope.
Okay.
No, I hear you fine.
All right.
But I have my like 23 to hear you.
Okay.
Yeah, I can hear the other students more clearly than you this time, but it's usually the other way around.
Okay. Let me see what I can do. Hold on one sec. I think if I had a setup just for teaching, I could nail all this stuff down, but I use my laptop for so many things. Let's see. Let me check Zoom actually. So let me take that off. And testing 1, 2, 3. Let's switch this.
You sound a fair bit loud now.
All right, yeah, we'll go with this. Share my screen.
Did somebody else have their mic on?
Looks like people are mostly muted unless they're talking.
I asked a question in chat about statics.
Statics usually pop up when you're using globals. And so ask yourself this question: what if the person wanted to create 10 queues using your code? Would it still work? And if you have sort of a single, if you have like a single static tail pointer, that's going to be a problem. But if you have a way to sort of have multiple tail pointers, then you might be able to make it to work.
Yeah.
Does that make sense?
Yeah.
Okay.
It's a little hard without a member variable,
Yeah, there is at least one or two ways to do it that I thought of, but like I say, they're pretty non-standard. And if you're not sure, do it the way that works, which is just to traverse the whole list. Turn that in for coding, but then you can have an alternate version if you want, functions 2 or something, and give me a readme and say, hey, here's where I tried to, use a tail pointer. And I'll look at it and let you know what I think, and it won't cost you your grade.
Could like malloc some sort of extra special struct and index index like a... I don't know if you could apply static to a dynamically allocated thing. Maybe you can.
You can. That might be another way to do it, is to have, you know, sort of a separate global structure that's part of your linked list package. And yeah, your static could refer to something in dynamic memory. So that might be a way to do it too. All right, other questions? All right, well, let's continue. Oh, there's a series of quizzes posted on Canvas. They've been up there since, you know, December. And those have due dates on them. Those due dates are the dates by which I believe you will have, you know, gotten enough material to be able to do them. But most of those quizzes are doable, you know, before the due date. And as soon as you feel like you have, you know, the information to do those quizzes, do them and just get them out of the way. And if you have questions, you know, about them, ask in class or ask in office hours. Don't, you know, look at a due date of N and then look at the quiz on day N-1 for the first time, and then, you know, try to get it done in 24 hours or something. Look at those things ahead of time, and you know, a lot of them you're already able to do. And so I would say just do those as soon as you can, get them out of the way. If we're getting close to a due date and you feel like you don't have what you need to answer, you know, some of the questions, ask about it, and we can talk about them. All right, well, let's go back to hashers and hash tables. And I'm not sure exactly how far we got last time, but let's just kind of rehash the basic setup here.
We got through associative arrays.
Okay, good, thanks. So an associative array, you know, is something like a traditional array, but instead of indexing it with consecutive integers starting from 0, we can put in, you know, maybe something like a string or a license plate or you know, some other type of thing that acts as an index. And using that, we can store and we can retrieve information from the array. And so when we do this in Bash, it's called an associative array, and there's some quirky syntax we use to set these things up and, you know, access elements and stuff like that. But the idea is the same whether we're doing this in Bash or Java or C or abstractly. And so part of this is built around the idea of a key data pair. And so a key is the thing that you use to retrieve or access a piece of information, which is the data. So it's typically, you know, data bracket key, or let me not call it data. Let me just call it array bracket key equals data. So the key is like the index. And the data is the thing that's stored at that index in the array. I'm going to mess with this a little more. Okay. So if we had, you know, our license plate example, where we want to store license plates and names of people who own, you know, the cars with those license plates on them, we could use an associative array for that. So we could have an array called plates. And we would use each license plate as a key, and we would store as the data the name of the person with that license plate. And this gives us a way to search for information. So if I want to know who owns this license plate, I simply try to access an element from the array with that index. I use that key and I see what data comes out. And if I get something out like Nick, I know Nick's the person who owns that. And so we talked about a strategy for doing this, which was to basically make plates a kind of traditional array. And then we have something called a hash function. And we can put a key into there. And what comes out is an integer, an index, like a 3. And that 3 means the data associated with that key is stored at index 3 in this plain old array. And so down here we would find the name Nick. So the hash function is a map from this sort of associative magic where we can index with arbitrary things into a plain old array that we index, with consecutive integers starting from 0 and going up to whatever the length of the array is, -1. So it's our mapping. And this works great in theory because, we might have 1 million license plates stored in this array. And when I want to know what's the name associated with this particular plate, I don't have to search. I simply run my plate through this hash function, I get out an integer, I go straight to that location, and there's the data. And so in theory, this is an order 1 system. We can store, we can retrieve, we can search with a fixed amount of time, no matter how much data we have in the table. The problem comes when we have, different keys that might give us the same index from our hash function. And so if I had another license plate, CAB123, maybe my hash function was not written very well, and it gives me an index of 3 for this. And so if I want to store, some other name associated with this license plate, my hash function would say, hey, you should store that right here. But guess what? That spot's already in use. So I have a problem now. I either store my new information here and I lose my old information. That's no good. Or I tell the user, sorry, something went wrong. I can't store your information. And that's no good. Or I find some other place to store this new information, even though my hash function says store it right here. And that's what we want to do. So these are called collisions. Collision happens when two different keys are mapping to the same location. And this is guaranteed to happen if we store too much information in our table. Typically, if a license plate was 7 characters long, and if we suppose there's, 40 characters you can choose from, well, if we have 7 characters, that's 40 to the 7th possible license plates, right, which is a huge number. And if my license plate database only holds 1,000 things, right, I can't fit 40 to the 7th pieces of information into an array that only holds 1,000 names. It's just not going to work. It's pigeonhole principle. So inevitably I'm going to have collisions if I try to put too much stuff in. But the way that we write this hash function can help to minimize collisions until we simply have too much stuff in. So maybe my hash function is just saying, let's look at the last digit, and that's where we're going to store the name. Well, that's a horrible hash function, because the last digit is, only 10 possible values. I'm only going to use 10 elements in my array. I've got another 990 there going to waste. Maybe my hash function is to add up the ASCII codes for all of my characters, and that's a better hash function, but you know, this license plate and that license plate will hash to the same value, because adding the ASCII codes for A, B, and C is the same as adding the ASCII codes for C, A, and B.
So in this case, could you just add up like the last 4 digits? Because those would be different.
I could have a hash function that adds the last 4, but for these 2 plates, again, those would hash to the same thing.
Well, because you have ABC and then CAB, so you'd have C123 and B123, which would be different, right?
Oh, you mean do the first one and the last 3?
Yeah, I mean, like, yeah, so like the first one in front of the hyphen there, and then the last 3 digits.
Ah.
But then again, I guess if you add BA and AB,
right,
it would still be the same thing. So.
Yeah, so it's a good idea, and it gets to the essence of, you know, how do you create a good hash function, and it really depends on the data. It may be that all of our license plates start with ABC, in which case, you know, I wouldn't use this as any part of the hash function. It may be that all our license plates, you know, are 3 letters, a dash, and 3 digits. Well, if I know that, I can do something with that information to make a better hash function. So this is, you know, a good question, and it's a question we're not going to dig too deeply into. On your assignments, you'll be given a hash function, and if you're writing your own hash package, you know, for Google or something, there will be a team of, you know, mathematicians who will figure out what a good hash function is based on the data requirements. But we want to just kind of understand some examples of them for now.
It seems like it would be really rough to try to come up with some hash functions that would efficiently use the data in the array, but still let you put in whatever kind of key you wanted.
Mm-hmm. Yeah, so if you're hashing words, your best hash function is going to be different from if you're hashing student IDs or phone numbers or license plates or, you know, snippets of WAV files from songs. Those would all have very different characteristics. And those are all good things to hash, right? This is a great way to do automatic tagging of music files. You take a snippet of the song, like, you know, the first half a second or the first 2 seconds or something, and you turn that into an index. And in that location, you store information about the song and the tags and so on. And now, you know, if you want to know what song is this, well, you don't have to compare that snippet of your WAV file to 10 million possibilities, right? You run it through your hash function and it says, oh, you know, that's stored down here at location such and such. You go there and there's the information associated with that song. So yeah, different hash functions for different data types probably make sense. Although at some level it's all binary data. But, you know, if we were coding student IDs...
Sorry, that's not exactly what I meant. I was talking more like you're talking about tailoring hash functions to meet the demands of how your data is going to be presented.
Mm-hmm.
Does it make sense if you have several different groups or ways that your data is going to be presented in the same larger group to like have a hash function that tells you or can instantly grab the like most optimal hash function to use for different data sets?
You might be able to, but in practice you probably have a single hash function for... I don't know if people do that. The hash packages I've worked with have sort of, you know, one predefined hash function. I don't know if there's packages that will sort of tune that or select from a batch of options on the fly. You would think there would be, but I'm not familiar with one. But yeah, I think that would make sense. Alright, so we want to talk about more about hash functions. We want to look at some examples. We want to talk a lot about collisions. and figure out, how do we deal with this business of, two different keys mapping to the same place. And there's two ways to deal with that, and we'll talk about both of those. But let me back up a bit. And let's talk about hashes as abstract data types. So we have this notion that, whenever we develop a data structure in this course, or we encounter a data structure in the wild, right, we want to understand the abstract view of that structure in addition to understanding how we're going to actually write code to implement that. So with a linked list, right, the implementation is, mallocing a node and having a sentinel and using the next node and looking for nulls and all that stuff. But the abstract view of a linked list is simply, something that we can put things into, we can remove things from. And we can search for something, we can insert something before a node, and so on. A stack, the abstract view, is simply a LIFO. It's a collection of things where we can retrieve the last thing that we added to it. But the implementation is, we've got an array and we've got a stack pointer and we add one to the stack pointer when we push and all of that stuff. So before we go into the details of implementing a hash, let's make sure we're clear what an abstract hash looks like. So disregarding how this works, what do we want to do with a hash? We want some kind of initialization. We always need that. Whatever structure we're going to use, we want to be able to say, give me, a new one of these structures. So some sort of init function. And then we obviously want to store stuff in the hash at some point. And we'll usually use the function name put to say, let's put something into the hash. And if I'm going to put something in the hash, what are the two pieces of information I need to specify?
The key and the data.
Mm-hmm. Exactly. So I need to say, what's the key and what's the data associated with that. And so init, maybe returns some form of a hash, probably a pointer to a structure. Put, maybe it returns an integer saying did it succeed or not. Because, your hash could be full. But the basic action is, here's a key, here's a data. Store this data in the hash associated with that key. All right, to retrieve information, we usually use get or fetch. So I'll say fetch. So I'll fetch a key, and this should return the corresponding data. And, with a regular associative array, if we try to access an element that doesn't exist, it doesn't blow up or crash. It simply gave us back an empty string in bash. And so maybe we would do something like, have the fetch function return null if the key is not found. Or you could, pass an argument that says, did I succeed or something. But somehow, we want to take a key and say, give me the data associated with that. And we also want to know if there was no data associated with it. So if we're looking for license plates, we put in a plate and it's not in the database, it should do something reasonable. And so we might have, a search function which says, is the key found? But chances are, if we're doing that, it's because we want to fetch the data. So usually search is taken care of by fetch. We might also want to delete. So we could say delete this key from the database. And maybe we'll return a flag or maybe we'll trust the user is not going to delete something that's not there, but functionally some way to delete something. And so at a bare minimum, right, initialize, put, fetch, and delete. And you could have other functions. You could have something for, you know, clear out the entire hash, delete everything in there. You could have something which says, tell me how many things I have in the hash. There's all kinds of other functions we might have that probably aren't strictly necessary if we have one other function. And what's a function that's missing in a pretty major way from this list? Something that we had for linked lists. And that we made for hashes and queues for PA2, for stacks and queues. Anyone notice anything missing?
Like a print?
Yeah, something like a print, right? We want some way to see what's in the hash. This will let us, you know, go out and you know, put a license plate in and get back a name. But what if we wanted just a list of all the license plates and all the names associated with them? There's no way to do that with just these functions, because if you don't know the license plate, you can't say fetch the data associated with that. And this is one of the aspects of an associative array. Because the indices are not consecutive integers starting from 0, there's no automatic way to say, hey, give me all the elements from this array.
You could have some sort of key cache, I'm sure.
Yeah. So we did something like that in Bash. We had a way to iterate over the keys. And we used this, you know, for in structure. Where we got, you know, a space-separated list of keys, and then we could say for, you know, next key in this list, and we could retrieve those keys one at a time. So we're missing a way to, you know, traverse the data. Traverse is a fancy way of saying, you know, go through the data one at a time. And so with hashes, we're going to introduce a concept called an iterator. And we can always have an iterator for any data structure we make. And the idea of the iterator is it's a way to systematically request one piece of data from your structure, right, one at a time, such that you eventually access all the pieces of data without any repetition. So for an array, we don't need this. For I equals 0, I less than 10, I plus plus, give me array bracket I. That's very easy. For a linked list, we don't need this. We start at the sentinel, we just move down the list until we get to null. But for a hash, we need some way to say, hey, you know, what's the next key in your hash? So iterators usually come with a pair of functions. So we could have, you know, initialize the iterator, and then some kind of like next key function. And here's how this works. When we want to start going through all the data in the hash, first we call initialize iterator. And that sets up some sort of internal housekeeping. And basically says, all right, we're going to, you know, give the user all the data contained in the hash. We give it to the user one piece at a time, and we do that when they call the next key function. So you call a init iterator, you call next key, and this function will return some key from the hash. There's no such thing as a first key or a last key. It's just some key. And there's usually never any guarantee what order these keys are going to come to you in. But you'll get some key. And the next time you call next key, you'll get some other key. And the third time you call it, you'll get a third key, and so on. And maybe we could define this to be, you know, null if there are no more keys. And then if you want to go through the data again later on, you call an iterator and you start calling next key again. And this is a really general concept, and a lot of data structures come with some sort of iterator. And it's a whole class in Java, and things like, you know, hash tables and so on support iterators for going through them. So we'll work with this a lot.
So I have a question for you about the abstract data types.
Okay.
So are we trying to get at the fact that every kind of data structure we would want to use is some kind of abstraction from an array or a linked list or a struct? Like, at some level, they're built on top of those structures. It's just how we're organizing that data?
Not necessarily. The idea of the abstract data type is to be able to talk about a data structure regardless of how that structure is coded. So it's the part of the data structure that is independent of the actual coding. And so the fact that there's a put method that takes a key data pair and returns success, well, that has nothing to do with how we're going to actually create a hash in C. Whether we're going to, you know, write the code that we're going to do in PA3, or we're going to use the GDBM package that's part of Unix, or we're going to, you know, send text messages to someone on an island and they're going to write down on paper each key data pair that you store. Regardless of the implementation, right, we have this function for storing, we have this function for retrieving, and so on. So the abstract data type view is talking about the aspects of a data type that are independent of how it's implemented. So the view of a car as an abstract entity would be, you know, a machine that you can sit in and you can cause it to go faster, you can cause it to slow down, you can change the direction in which it moves. Right? The specific implementation would be, you know, this car versus that car versus some other car. But as an abstract, right, we understand what a car is. And if we understand the abstract notion of a car, we sit in a car we've never driven, we can still drive it. We just need to know, how do I make it go fast? How do I slow it down? How do I change the direction? Does that make some sense?
Yeah.
Okay. And the more we do this, the more we develop data structures, the more I think that concept will solidify. And then when we get to 223, where we're just working with data structures that are already coded for us, then we'll have some very direct experience with, you know, working on this side of the firewall, where we're just concerned about the interface. 222, we're mostly on the other side of the firewall. We're implementing these functions, we're writing the code for them. All right, so an iterator is a really useful construct. So for example, if I wanted to, you know, print data from the hash, let me do this on a new sheet. Let's print the hash contents. Well, I could do something like, you know, init iterator. And then I could say, you know, key equals next key. Well, key is not null. This is pseudocode, right? Well, I've got a key from my hash, so I could say, let's fetch the data. associated with that. Let's print the key and the data. And then let's get another key. So I initialize things, I fetch my first key, assuming that there is at least one key, I'll get the data associated with that, print out the key data. Now I'll ask for another key. If there was another key, so it's not null, I'll fetch the data associated with that, print out the key data pair, ask for a third key. If it's not null, I'll get the data, print it out, and keep going. Once I've done this and I've printed every key data pair from the hash, my next key will return null. I'll kick out of my while loop, and I'm done printing. So even if my hash package doesn't come with a print function, and it probably wouldn't because there's so many different ways to print, right? Even if it doesn't come with a print function, if I have an iterator, I can use that to cobble together a really simple loop that will let me print, and I can print in whatever format I want. And the print functions that we used, for our linked list package, are kind of artificial because, we printed out a space-separated list using %d to print an integer. Well, that's what I wanted you to do, but somebody else might want to see that data, one number per line. Or they might want to see 5 numbers per line. Or they might want to print the numbers until you've printed 72 characters and then go down to a new line. And unless you're going to write 100 different print functions, right, you're not going to be able to satisfy everybody who wants to use this package. So you could provide an iterator, and now the person has a really easy way to go through the list and pull out the data without having to understand how the list is implemented. Right? If you didn't do this, the only way that somebody could print the contents of a linked list would be to go to the Sentinel node, right, and then follow its next node to the first node of the list, and then find the data field of that node and print it out, and then follow the next node to another node, and keep going till you get to null. And now they're on the wrong side of the firewall, right? They're tinkering with the internals of how a linked list is implemented. So an iterator like this lets you access the data one piece at a time without having to, do anything other than the high-level interface functions that define the linked list, or the hash in this case, as an abstract data type. And this is another example of stateful programming, right? You're going to call this one function next key, but it's going to do something different every time. And its behavior is going to depend critically on whether and when you call this function. If I call next key, it may give me the next key, or, if I call an iterator first, it's going to give me a different key. Alright, so that's just something to keep in mind is this sort of user view, the higher level view of what a hash table is. So let's go back to looking at collisions. I put too many letters in usually. And so remember, our hash is basically an array, a traditional array. So here's a tiny hash table. It only holds 10 things. And let's hash license plates by using the last digit of the license plate. Horrible hash function, right? So, but we have a plate, and we put it into our function h, and we get out an index.
I have a question as we're going through this.
Sure.
This is more of like out of curiosity for
Mm-hmm.
implementation. So, would it be possible to have some kind of secondary hashing layer to save on space and efficiently organize something? Like, let's say you have a hash indice that spits out a 4, and then your next one spits out a 10, and you have some sort of array to store those with integers. And since integers are smaller, you could then like have at each index from the hash, the first hash, into an array that stores like a sequential number for your actual hash table.
Maybe.
Yeah.
I would have to
Would you
think
have
about
some
that.
sort of multiple level like hashing?
Yeah, if I follow you, I think that is feasible. I would have to think about the details.
Between a hash table that's like if you're taking each of the things and you're organizing it based on like modulo,
Mm-hmm.
what's the difference between that and like just a basic array? Isn't it just storing it in
the implementation of the hash table really is just an array.
Okay.
But I might take a license plate like, ABC123, right? And I can't use that directly as an index on an array. I have to turn it into an integer index somehow. And so my proposed horrible hash function here is just take the last digit and treat it as, an integer. So if it ends with the ASCII character 3, we'll store it at index 3. And I'm doing this not because it's a reasonable hash function, but just because I want an easy way to hash these, because I want to look at collisions. And I don't want to get bogged down with adding up ASCII codes or fancy arithmetic or things like that. So let's suppose we've got license plate ABC123 and this is associated with Nick. So our hash function looks at the plate and says, oh, let's use index 3, and it'll store Nick right here. And then we have EE567, and that's Izad. And our hash function looks at this and says, oh, let's store that at location 7, and so this is where Izad gets stored. Alright, and so far so good. So far, if I've got a license plate like ABC123 and I want to find whose name it is, I don't have to search, right? I just look at that 3, I go directly to location 3 in my array, and bingo, there's my data. It's like magic. But the pretty clear problem is, I have TUV483, which belongs to Trudy, and I run this plate through my hash function, and it looks at that digit and it says 3. Oh, we should store Trudy right here. And we can't do that, because this space is already in use.
Now, at that point, if you don't have any of the logic there, would it that just like halt?
If I didn't do anything special, it would simply overwrite the data that's already here.
Oh, okay.
Right, so 3 should be a valid index. And remember, with arrays, in most languages, there's no such thing as an empty element in the array. There's always bits everywhere in memory. So there's something stored in all of these locations anyway. So we really would need, some kind of extra flag to say, hey, this spot is in use. And we'd initialize those to zeros, and then when something gets stored there, we could set that flag. So hopefully, when we try to store this name at location 3, the system realizes, hey, something's already stored there, and we have a collision. And so one really easy way to manage this is start looking for the next available spot. In this case, we could check the next spot 4. That's free, so we can store Trudy there. So things just got a little more complicated, because now if I want to find what's the name associated with TUV483, I take that index for 3, I come out here to my array, I see Nick. Well, if I return Nick and say that's the person who owns that license plate, I've got a problem. So I need to have some other information in here. I need to store not just the data, but also the key.
So does that mean those are going to be stored as structures?
Those are going to be stored as structures, yeah, most likely. So in my array, I'm going to have not just the names, but I also got to have the keys themselves, the license plates in this case. So when I say, hey, I want the data associated with ABC123, I take that digit 3, I look at index 3, I see a name, I check the key, and it says, oh yeah, this is the name for ABC123. When I come in with TUV483, that 3 says, okay, look in location 3, I look there, there's something there, but I check the key, that's not TUV483. So I have to assume maybe this data is in the hash table, and it tried to get stored here, but it ran into a collision. If that happened, it would have been stored in a different location. So I check the next location, it's got something in it, I check the key, hey, TUV483, I found my data. But it took me 2 sets of operations now. I didn't just take the last character, treat that as an index, retrieve my data. I had to do some other stuff, and in this case, I had to do another search at the next location. So our order of complexity is going to suffer. It's not going to be order 1.
And like you said last week, with hash tables, theoretically it should be order 1, right?
Theoretically, it should be order 1. If you don't have collisions, it is. But collisions stop that from being the case.
And I may be getting a little ahead of ourselves here, but is there a way to effectively make sure that collisions can't happen? Or
Not really.
Is that pretty much impossible?
It's pretty much impossible unless your hash table was as large as the space of possible keys. And that's usually not feasible. Like I said, 40 to the 7th possible keys, unless your array was that big, you're always going to have the possibility of collisions.
Well, now these big, like, databases, like these big server rooms that are just packed full of, memory machines, basically. I mean, is that what they're doing? Is they just have so much memory set up for these, like Google, even?
Mm-hmm.
Like the Google server rooms? They just have so much memory set up that it's basically making it impossible kind of a deal, or
it's probably not making it impossible, but it's making it manageable.
Okay.
So if I knew that, at most I was going to have to go to a location and maybe go one more spot, right? It's going to take twice as long as if I don't have a collision, but that's still technically order 1. The problem is, if I increase this, if I increase the amount of data in my hash by 1,000,000x, what's going to happen to my order of complexity, my performance? If it's going to double, that's not a big issue. If it's going to go up by 1,000,000, that's a huge issue. And so companies that deal in data, part of the goal is, how do their storage systems adapt as the amount of data grows, so that, your hash table gets larger quicker than your data starts degrading your performance.
This seems like a really interesting engineering problem.
Yeah. That's probably an understatement. Because, this is the kind of stuff that made Google. Google was a search engine that, 2 people were just kicking around ideas and were like, hey, let's try this. And it was tiny, everybody used Alta Vista and all these other engines. And
Yahoo.
Yeah, right? And I don't think any of us anticipated that, something as simple as a fast search algorithm would you know, not just change Google, but would literally change the world. I mean, it's such a different society we live in now, and it's largely because of, you know, what Google has exposed, for better or worse. But yeah, so this is definitely a interesting engineering problem.
Yeah, it's crazy to think when I was a kid, we had encyclopedias. Google wasn't even out yet.
I know, right?
And then now we can literally, like, me and my wife were actually talking about that, where, you know, you used to talk to somebody and go, you know, I wonder, you know, what's the answer to this question? You go, well, I don't know, and you just move on.
Yep.
Now
Yeah.
you Google it and you get the answer, you know?
Yeah. I'll wake up in the middle of the night and Google stuff that, like, I can totally live without knowing.
Oh, for sure.
All right, so so there's a collision, and this can get worse, right? So you know, ABC 453, and that's Phil. And so we look at the 3, and that should hash over here. Well, that spot's in use, so we can't store Phil there. We check the next location, that's in use. Can't store Phil there. We check the next location, that's free. I added an in-use flag, right? So this spot's available, so we'll store Phil right there. We'll store Phil's license plate. And we'll set the in-use flag to 1.
And the in-use flag, that would be stored inside the structure?
That's part of the structure too, yeah.
Okay.
All right, so what happens when we try to retrieve information? If I try to retrieve Nick, no problem. If I try to retrieve Phil's information, I'm going to look at that 3, I'm going to go to index 3, I'm going to check, I look at the key, that's not the key that I'm looking for. I'm looking for ABC 453. But maybe when I tried to store Phil, there was a collision. So I'll go to the next location. That's not the right key, but maybe there was a collision there also. I'll go to the next location. Hey, there it is. Now, if I try to fetch, you know, dog 773, I go through the same process. I take the 3, I go to index 3. There's some data, but it's not dog 773. Maybe there was a collision. I check the next one. Nope. I check the next one. Nope. I check the next one. It's not in use. At this point, I can say, hey, dog 773 is not in the hash. But I only know that because, you know, I didn't find it at the place that it should have hashed to. And I checked all the subsequent places that it might have gotten stored based on finding collisions when I tried to store it, until I got to this empty spot. And so now I know 773 is not in there.
And the traversal through the table, that's part of your hash function, right?
That's part of the hash function. That's going to take care of that for you.
Okay.
And it's going to slow things down. Oh, this, by the way, is called probing. This is one way of dealing with collisions. This is not the way you're going to do on PA3. But this is definitely a way you want to understand. So we're basically probing the table to find a different spot to store your information. And it's complicated because, for example, suppose I delete ABC123. Alright, so I take the 3, I hash it to index 3, I look in that location, it's occupied. That is the key, right? How do I delete? I just change the in-use flag to 0. So that now, you know, if I want to store something at location 3, I can. But now if I say something like fetch ABC 453, what does my code do? It takes the 3, goes to index 3, looks in there, and when it looks here, it says, hey, this spot's not in use. Well, if I don't do something more clever, it's going to say, sorry, this is not found in the database. So I need to know that, yeah, this spot is not in use, but it was in use before, and it might have caused a collision. And so I need yet another flag which I'm going to call deleted. And I'll set that deleted flag, and when I try to fetch something, and I go to an index, even if it's not in use, if there was something there, I'm going to say, hey, maybe there was a collision when that data got stored. I'll check the next location. That's in use. I'll check the next location. Hey, there's my key. So this gets more complex.
So that's just going to be a conditional being like if your delete flag is equal to 1, then kind of traverse down.
Mm-hmm. Yep.
And check some more. Okay.
Yeah. So we'll whip up some pseudocode for this probably after the break. But let's talk more about this idea of probing. This is a very simple approach to probing, which is called linear probing. And it's the simplest kind of linear probing, which is, you know, if I can't store it at the location I want, try storing it in the next spot. If I can't do that, try the next spot. And just keep trying until you find an open spot, or you run out of spots, in which case your hash is completely full, right? So that's one type of probing, but it's not a very good choice. And the reason it's not a good choice is because of this right here. Right? We've got 3 names that we stored, and they're all sort of clustered together. And we're not using any of this space, we're not using any of this space. Now this is a small table, right? But if this table was 1,000 elements long, these 3 names would have gotten all jumbled together right here around index 3. And so there's this idea of clustering, which is where you have maybe a large amount of space in your array, but your data gets gummed up in these little clusters of collisions. And so you have lots of empty spaces and then lots of like dense spaces. Yeah, go ahead.
Would there be any way to like thin down your array a bit? Like maybe reallocate some space after your current indices, but cut all the like spaces in the middle of your stuff?
You could try to rehash it with a different hash function. You can grow your table, and we'll talk about doing that. But you can also use a better hash function to begin with, and avoid some of this trouble up front.
There's so many ways you could tackle this problem. It's so cool.
Yeah, it's a beautiful area actually of computer science, and I think I mentioned in 224, right? When I first encountered the idea of a hash table, it became my sledgehammer, and everything I had to do, I changed into a hash table problem. And for a couple of years, that was like my go-to tool. And I used it to write compilers and loaders, and to do indexing, and to do syntactic analysis on code, and all kinds of stuff. And it's such a powerful mechanism if you use it in the right way. And there's something really compelling to me about associating data and keys, as opposed to having to search. Because searching, even when you can write a search algorithm, I think internally we know this is like going to take a lot of CPU time, it's going to take a long time, and all this sort of stuff. And being able to just go in with something and retrieve a piece of information is like, there's something powerful about that. All right, so let's look at a general form of probing. And we can think of this business of, if we can't store our data here, let's try the next location, let's try the next location. Let's rethink that. Instead of just saying we're going to try the next location, the next location, and the next location, let's think of it as rehashing. let's imagine we have different hash functions. We have a hash function we're going to use initially, which, might take, ABC 453, might map it to index 3. And if we can't use that, we're going to rehash that same key to get a different index. Well, in this case, our rehashing was simply the original hash function plus 1. And if we had to rehash again, it would be the original hash function plus 2. And if we tried to hash a fourth time, it would be the original hash function plus 3. And so I want to think about a new hash function h, which takes two arguments. The first argument is the key, and the second one is the probe number. And the probe number is basically the attempt. Starting from 0. And so, our original hash function took a license plate, gave us back the last digit. Well, our modified function would be just take the last digit of the key plus the probe number. And I'm going to reduce this whole thing modulo 10, because if I get a license plate that ends with a 9 and I'm using a probe number of 1, 9 plus 1 is 10, I don't want to try to store it in location 10, I want to try to store it in location 0. So I'll do a modulo 10 to roll things over from 9 back to 0. And so all of this probing business can be thought of as simply a modified hash function that takes not only the key but also an attempt number starting from 0. And the idea is each time that we hash our key with a different probe number, we should get a different value, a different index to try to use.
It seems like it's something you would try to avoid, though, because you could have the potential to walk the entire hash map or hash array. Right?
To do what with the entire hash array?
If let's say you put in A as your first key, right? And the next key is like a B or something like that.
Okay.
You need to see, hey, there's already a collision happening. Maybe walk to the next space in the array.
Okay.
Would that still be an ON complexity? Like you have to walk the entire array to find some suitable space because you're having so many collisions? Maybe unlikely, but is it still?
Yeah, I mean this will require, a higher number of operations. That number being the number of probe attempts it takes to find an open spot. So if you always have to, hash with a 0 and then hash with a 1 before you find an open spot, it's always taking you twice as long. If you potentially have to, try 100 different probes before you find an open spot, then you've seriously impaired your order of complexity. But the idea will be to try to find a way to generate a new index given a key and a probe number so that you minimize these repeated collisions. And so the function that we're using is, just take the last digit, add the probe number, reduce modulo 10. And that's giving us this clustering effect. So we could have a different function like hash of key and a probe number equals last digit of key plus, 3 times the probe number, and reduce that modulo 10. So now let's try storing some of our data. So let's put ABC 1, 2, 3 and Nick. And so the 3 hashes to index 3, so we'll make this in use. It's not deleted. We'll store Nick, and we'll store the key ABC123. And then Izad goes in EE567, so that'll get stored down here. There's Izad. There's EE567, and it's not deleted. And then we did Trudy with TUV483. So TUV483, well, we'll hash this with a probe value of 0, which says take the last digit of the key. That's a 3, plus 3 times the probe number, 0. That's going to give us a 3. And location 3 is in use. So we're going to rehash with a probe value of 1. Well, our hash function, right, is take the last digit, which is 3, and add 3 times the probe number. Well, the probe number is 3, is 1. 1 times 3 is 3, plus 3 is 6. So we would store this license plate at location 6, which is available. So there's Trudy, and there's TUV483. And then we store ABC453 for Phil. Well, if we hash with a probe of 0, that's going to bring us to location 3. That's a collision. If we hash with a probe value of 1, that's going to take us to 3 plus 3 is 6. That's a collision. If we hash with a probe value of 2, that's going to take us to 3 plus 6 is 9, and that spot's open. So we'll store our data here. There's Phil. There's ABC453. And so our data is more spread out, right? We've avoided this big cluster of data around 3, and this is likely to improve our performance. And this is also an example of linear probing, because we're just using a linear factor on the probe number. But we might do something like add the square of the probe number. So that would be quadratic probing. And yeah, go ahead.
Go ahead. You could do something like what a vector would do and reallocate the array, and then you have all that free space way up ahead, and you could trade off that space for the performance, right?
Mm-hmm.
And try to hash way out there or something.
Yeah,
like
yeah.
That, right?
That's the classic trade-off always is speed versus time versus space, basically. So yeah, if this is a silly example because it's only 10 elements long, but if we imagine that this was 1,000 elements long, right, it would take a lot more insertion before we would start getting a lot of collisions. But at some point, this table will become more and more full, and collisions will happen more and more often. And so we can talk about the load factor, which is basically how much of our array is in use. If our array can hold 1,000 entries, and we've got 350 of them in use, our load factor is 35%, or 0.35. And a good package will do things like monitor the load factor, and if the hash starts to get full and it starts to realize that collisions are going to happen more and more often, yeah, you could grow the array. Instead of having an array that holds 1,000 things, you could make a new array that holds 2,000 things. Modify your hash function so it will use all 2,000 locations. So, reduce modulo 2,000 instead of 1,000. And then go through all the data in your current hash, rehash it with your new function, store it in the new array. And this can be happening in the background, right? The user never knows this. They put something into the table by saying put, and it started a background process of making a larger hash table, rehashing everything, and then switching over to that bigger table. The only thing the user ever sees is that, hey, the next time they put something in, it runs a lot quicker, right? But this is all done kind of behind the scenes. All right, let's do a 5-minute break, and then let's go through some pseudocode for what we've just described for how we can search and insert and delete using probing, and then we'll move to thinking about another way of handling collisions, which will be chaining, which is what we'll do for PA3. So let's come back at just about 5 minutes. That lettuce because I needed to get up to $35.
Oh, okay. Yeah, lettuce.
This was all triggered by thinking about getting oatmeal. When I went to look, it said, "How about some Mexican drugs?" Which means that they were in stock.
Oh, yeah.
So I put those, and it kind of snowballed from there.
Yeah.
It's really like early morning.
Are we out of oatmeal? Oh, yeah. The big.
That's okay. I don't mind if people know that I eat oatmeal.
No.
I'll use this one. Alright, welcome back. Alright, so we have our hash table. It's an array. It's going to need to store a bunch of information. It's going to have to store the data, obviously. That's the main payload. But we also need to store the key so that when we find a piece of information, we know whether it's the thing we're looking for or it was something that got into that spot first. And we need to store an in-use flag because we can't just look at a spot in an array and know if it's being used or not. And we need a deleted flag to help us deal with searching for things that that originally collided with something that's no longer in the table. So our array is going to be an array of structures. So let's look at a pcode for doing a hash table with probing. So I'll imagine a structure for a hash entry. And what's it going to need? Let's just suppose the key and data are strings. So we'll have a car star key, a car star data, and we'll need some flags. So I'll do an integer flag for in use and an integer flag for deleted. And so that's the basic entry. Each row of our array is going to be one of these things. So it's got those 4 pieces: key, data, and a pair of flags.
Could we do, like, if we wanted to, let's say, a pointer to some data so that we could minimize down the array, you could compare the size of the array?
Mm-hmm. So we can set up the array a couple of different ways. If we don't want to do that, if we just want a fixed size array, we could say something like, struct hash entry hash bracket 1000. But we don't really want to do that because that forces the size of the array to be 1000. It's pretty hard to expand it. And we may want to start the hash small and grow it as it gets more full. And pretty much everything we do in this class, we really like pointers. So rather than declaring our hash like this, we're just going to say struct hash entry star hash. And an array is a pointer. We're just being explicit here about, this thing is a pointer to a struct hash entry. And if we do this, then we need to actually make it point somewhere, and so this is where we would use a malloc. And we'd say hash equals malloc. And I don't know how big we want it to be, hash length. So we'd have some initial value for that, so our malloc would be something like hash length times size of a structure hash entry. So that'll take how big one of the elements of our array is, multiply by the number of elements we want, allocate that many bytes, hash will take that value, and so now this is pointing to not just a hash entry, but the hash entry at the beginning of a block of this many hash entries. Alright, so what do we have to do for a init? Well, this might be part of our init function. And to really initialize this, we need to make sure all of these in-use flags are 0, and we probably want to go through and make the deleted flag 0 also. Now there's a lot of different ways we can actually put all of this together, but I'm going to do a pretty straightforward, not thinking too deeply kind of approach.
the reason for not for having a deleted flag again? Wouldn't you just have the in use be 0?
Because if we delete Nick and we set the in use to 0, and then we look for ABC 453, when we come to location 3 and we see that's not in use, our search would stop at that point and say, oh, I guess it's not in the table, because if it was, it should be right here.
Okay.
And our code wouldn't see a reason why it couldn't be here unless we know, oh, there was something here before, because we see that from the deleted flag.
Okay.
So, you know, for I equals 0, I is less than #len I plus plus. What do we want to do? Hash bracket I dot in use equals hash bracket I dot deleted equals 0. So that's probably all you need to initialize this. And so someone suggested in chat, why not have just a single flag that we have multiple meanings for? Because, you know, we got 32 bits here, we got 32 bits here. And yeah, you can definitely do this. You could have a flag where 0 means free, 1 is in use, and 2 means deleted. And that works perfectly well, and it saves you a lot of space. I'll do it like this just for a little bit extra clarity. But yeah, if you were actually coding this, you could do that with a single flag. Good. All right, so let's put something. And I'm going to assume that I have a hash function h, which takes a key and a probe number, and it returns an integer. So let's look at our put function. Put a key in a data. All right, so we'll initialize a probe value of 0, and we'll use our hash function to hash our key with that probe value, and we'll get back a location where we would like to store this key data pair in our hash. And we'll say if hash bracket location in use is 1. So if we are told by the hash function we should store at this location, but at that location we find something is already there, then what do? Increase the probe number and go back and try again. So this is the rehashing business. We'll set P to 1, we'll rehash, we'll check that location. If that's in use, we'll set P to 2, come back here, rehash, check that location. Assuming at some point we hash to a location that's not in use, that's where we store our key data pair. So now it's just, you know, hash bracket location dot key equals key, hash location data equals data, and hash location in use equals 1 to say that we're using this. And that's probably all we have to do. We might want to clear the deleted flag, but it's not going to matter in the end. So there's a basic put routine with one thing missing, which is, you know, what if there's nowhere to store our data in the hash table? What if the hash table is full?
You need to grow it?
We need to grow it, but before we do that, an even more basic need is we need to do something other than just loop forever, right? So we need to detect if we've done so many attempts that further attempts will be fruitless. And so we can do something like, you know, if P is equal to And what did I call it? Hash length.
Or you could have like some method for is hash full with a boolean.
Right. So we could keep track of how many things we have in our hash table and see if that's equal to the length of the hash. If p is equal to the hash length, it means we've probed so many times that we should have tried every possible location. And if we're still looking for a place, then we know that you know, we're not going to succeed in the future, and so that could kick us out. We could also, you know, check to see if the location is the same as the location when we hashed with a probe of 0. And if it is, we know that we've looped back, and we're just going to keep, you know, trying the same locations again and again. But you need something in here, because if the table is full the way that this is written, we would just keep hashing for over and over and over again. And every time, no matter what our hash function returns, it's going to look like that spot's in use. And so this would be an infinite loop, and your put function would never return. So and this will be, you know, something we need for all of our functions, but I'm not gonna spec it out beyond that. But that's a basic put function. So the fetch function we go in with a key, same basic setup. Have a probe variable that we start with 0, hash our key, and now we want to know if we look at that location, do we find our data in there? So there's a few possibilities. So if hash bracket location in use is 1 and hash bracket location dot key equals the key that we're looking for, then we found our data. So we can just return hash bracket location dot data. So this is the case where we hashed our key, we looked in the table, and we found the thing we were looking for. So that's success. If that location is not in use, and that location does not indicate that something used to be in there, then we didn't find our key. And so I'm just going to say we're going to return null, and the caller will understand that if this function returns null, it means the key wasn't found. If it returns something non-null, it's returning the data associated with that key. So if we come down to a location in here, and it's not in use, and it's not marked as deleted, then we know that data is not contained in the table. Right? That key's not found. So if in use is 0 and deleted is also 0, we're done. Didn't find your key. The other possibility is that either in use is 1 and we didn't match the key, or deleted is 1. And in either case, that means we need to rehash. So here we say try again, we increment p, and we go back up here and we make another probe. With, you know, the same requirement that we do something to make sure we don't infinite loop here. Make sure we're not just repeatedly trying again and again and again. All right, is this good so far? Deletion's not too bad. So set a probe variable to 0, hash your key with that probe, find out where your data might be stored.
Could you, again, not to skip ahead here, if you're deleting, wouldn't you just flip that one bit and not like touch the actual data? Just know that it's supposed to be nothing.
Yeah, all you have to do is mark it as not in use and mark it as deleted. And you can leave the data where it is if you like. But we still have to find where that data is. So if hash location dot key equals key and in use is equal to 1, because there might be stray data in here. We might hash to a location that used to have this data in there but doesn't anymore, right? So see if the location that we're looking at matches the key and is marked as in use, and if it is, then we want to delete this. So mark it as not in use. Mark it as deleted. And maybe return a 1, you know, saying we deleted something. And then the rest of it would look like this. Right? If it's not in use, or if and it's not deleted, then we have not found our data. It's not in our table. And so we could return a 0 saying, you know, sorry, this isn't in the table. Otherwise, bump up your probe number, go back. And if you have checked every location, if your probe number exceeds your hash length or something, then we could also return 0 and say your data is not in the table. But this is the main action of it. And just like we've seen with so many of these structures, right, if we do our code like this, when you delete something from the table, right, the data is still there. In this array in the memory of the computer is still this name and this license plate. It's simply been marked as, you know, don't pay attention to this. But unless we deliberately, you know, replace this with blanks or E's and U's or something, that data will still be sitting in memory. All right, how about an iterator? So if you were allowed to break the firewall, if you were writing a print function as part of, you know, this hash package that you're developing, so you're allowed to work with this array directly and the in use and deleted and so on, how would you print the contents of the hash? What would be the easiest way to do that? Let's say you wanted to print all the data key pairs, 1 per line. Could you do that?
You mean without having to go through each individual piece of the array?
Or that?
Well, I mean, yeah, you could do that. Just go through each one, and if it's a null, or if it's if it's a 0, then you just print it out.
Yeah, that's all you got to do, right? Make a for loop from 0 to whatever the hash length is, and if that entry is in use, print out the data and print out the key. Right? It's pretty trivial. So how do we expose that to the user so that the user doesn't have to know about the in-use flags and the data and key fields and all that? That's what an iterator does for us. So our initialize So we have something like, you know, some, you know, global variable in that package, make it static if you like statics, called next location, which basically says when the person asks for the next key, you know, what should be the next key that I give them. And my initialize iterator I'm just going to set next loc equal to -1. And we'll see why it's -1 instead of 0. So next loc, I'm going to say start looking after here. So my next key function which returns, you know, a key, can do something like this. Let's increment next loc. So go to the next location in your hash, and if that location is marked as in use, let's just return the key. Return hash bracket next location dot key. Otherwise, go back up here and try again. And that's almost the whole iterator function. We'll have to do one check in here. But basically, you want the next key, just start, you know, going from wherever you left off. I initialize this as -1, so I'll start off, you know, at 0. 1, 2, next loc becomes 3. It's let's say this is marked as in use, right? It's in use, so I'll return this key. The next time that you call next key, I'll increment next loc to 4. And it's in use, so I'll return this key. You call next key again, next loc gets incremented to 5, that's in use, I'll return this key. You call next loc again, next key again, next loc gets incremented to 6, it's not in use. It gets incremented to 7, that's in use, I'll return this key. So every time I call next key, I'm basically moving to the next location in my hash table that's in use, and returning the key from there. And the only thing that's missing is we don't want to just do this forever. So if next loc equals hash length, then we're done. So we'll return null to let the caller know, hey, we're out of keys. You've seen everything. So after we return this key, we call next key again. Next loc will change to 8, it'll change to 9, and when it changes to 10, that's the hash length, we'll return null. And now the person has, you know, called next key 5 times, gotten 1, 2, 3, 4 keys, and then a null to say, hey, you've seen all the keys. And so we can wire up an iterator pretty easily.
Would you say all of this is fair game for the midterm next week?
Yeah, definitely. So I'd like you to understand, you know, the concepts of probing and hashing. So if I gave you a hash function and I gave you, you know, a series of put commands, you could figure out where those get stored in the hash array. I probably wouldn't ask you to do a lot of writing of code for this, because we're not going to start coding hash functions until next week anyway, with PA3. But you should understand the concepts, and one thing I've heard from professors at WSU is, you know, they'll try to work with students on hash questions, and they come to me sometimes and say, don't you teach your students about hashes? And I'll say, yeah, we spend 1 or 2 weeks, but it seems to be an area that doesn't stick for some reason. So I'm trying to spend some time going through it with both the idea of probing and chaining, which will come next, and you're going to have a programming assignment on it. And so yeah, it's definitely an important topic, not just for here, but also, you know, for a university after Clark. And I'm curious if our textbook talks about it. Has anybody looked in the book to see what, if anything, it says about hashing?
I have not.
All I got to do is find my copy of the book. Wow. I've got it so well organized that it's hidden in plain sight. Text, there we go. So yeah, it looks like about 25 pages on hash tables. Starting with chaining. And so chaining is the way we're going to talk about next, where basically we have a linked list associated with each entry in the hash table, and we resolve collisions by just adding to the end of the linked list.
But then, how would you pick out an index in that situation?
Well, let's look at that next. All right, so 5.2 talks about probing, and they do linear probing. We don't have to worry about the analysis. This is what I was describing, some of the stuff you get into to look at the probability of collisions, and there's all kinds of good stuff in here, right? But this is the stuff that potentially makes my head hurt, but that I actually enjoy.
I guess at that point, if you're gonna put a linked list in an entry because you had a collision, the keys would probably still be different, right? If the hash is the same but the keys are different, you can use that to traverse your linked list.
Yeah. So let's look at chaining. So totally different approach to collision management, and the idea is we have our hash table. But instead of storing our key data pair directly in these entries, each of these is like a sentinel node. And initially they could be a sentinel that's just pointing to null, so it's an empty list. But when you let's go to for location 3. When you try to store ABC123 with Nick, you create a node with ABC123 Nick, and you point your sentinel to that. And then when you try to store TUV483 for Trudy, you hash it to location 3, you find the sentinel node, you go ahead and you store your node in that list. So maybe you do TUV483 and Trudy, and you just tack it into your list. And you probably tack it in the beginning because that's faster than tacking it at the end. But so basically, you know, when you want to find a key data pair, you take the key, you hash it, you find an index. That gives you the sentinel node of a linked list, and now you simply search that linked list for the key. And once you find that key, you can return the associated data. If you want to add,
off the complexity, right?
but the complexity goes down, right? It goes up, right? Because it's basically order n, right? If quadrupling the amount of data tends to quadruple the length of these lists, right? It's back to order n. But if you're only expecting, you know, a small number of collisions in any given location, and this list only grows out to be like, you know, maybe 5 or 6, well, that's probably livable, right? Having to do 5 or 6 operations instead of 1, that's something we can live with. But if it's going to grow longer and longer and longer, right, then we're going to be probably looking at like order n or something horrible like that.
Maybe you could like have, for each linked list in the chain, you could have some sort of load factor of their own, and if you like, if the hash result is the same and the load factor is whatever max you want it to be, you should go and find another spot to put the chain at, right?
Right. So you could you know, keep track of how long these lists are, and once they get beyond a certain amount, or too many of them get beyond a certain amount, or the average length gets beyond a certain average, then you could do something like rehash, right? Make yourself a bigger hash table, move all the stuff into your new hash with a new hash function, and then you know, your list would be shorter because you'd have fewer collisions. So this is pretty straightforward to implement in theory, right? If you have a good linked list package, right, which you've got your PA1 now, and you've done some work on it with PA2, so you've got a pretty good hash package, linked list package already. You can use that, and you know, each of these entries in your hash array is just, you know, a pointer to a struct my node, and you initialize it by setting each of these equal to a init, and they'll each be a separate sentinel node pointer. And then if I want to add to, you know, this linked list, I just pass this sentinel node pointer to my add function, along with the key data pair I want to add. If I'm searching for something, I hash my key down to an index. I find the sentinel node at that index, and I use that as the argument to my search function. So it really kind of builds on top of the functions we've already been using and that you've already developed. But it's pretty powerful. It also has the advantage that it's potentially unlimited storage. If we store our data like this, once we've said our hash can only hold, you know, 10 things, that's it. That's as much data as we can store. It doesn't matter how good our probing is. But with this, you know, even if our hash only has 10 elements in its array, these linked lists can grow, you know, until we run out of memory in the machine. So we could store a million pieces of data in this hash table. Now the performance would be really horrible because you'd have 100,000 elements in each chain on average, but you know, it doesn't limit the amount of data you can store.
It'd be interesting if we could have, you know, maybe some sort of type information and store like a void pointer, say, and just know what type to cast it to and get the data back.
And packages for this will do something like that. When we do this in Java, we use the idea of generics, which are kind of like what you just said. They let you operate on data of a undefined type and define what.
Got 'em too.
Who does?
C#.
Okay, cool. Yeah. So yeah, we can specify the type and have the same set of code work with different types of data. And we can sort of do that with void pointers, like malloc will return a pointer to different kinds of objects by returning void. So we can kind of do that in C also.
It's a little bit easier there because if I'm not mistaken, in Java and C#, there's like a base object class that stores type information, and then it's even easier from there, right?
I think so. I don't know if you need a particular type of base class. I mean, there's the notion that all classes are like extensions of an object. An object is sort of the base class for everything. But then you get into, polymorphism and stuff like that I don't want to get into. But yeah, Java will be fun when we get there. We're doing, the really hard version of data structures right now on purpose. Because once you do data structures in Java, you're never going to want to write this stuff in C, right? It's going to be so much more pleasant and convenient to do this in Java that this is really your only chance to sort of, force yourself to actually code this at a low level by hand. And it's kind of like, when you take calculus and you're learning derivatives, you don't just get, a derivative formula to begin with, take the exponent, put it in the front, subtract 1 from it, right? You work through, f of x plus delta x minus f of x divided by delta x, and you do the limits with delta x goes to 0, and you work through that, right? And it's painful and it's annoying, and you eventually find out the derivative of x squared is 2x, right? Why do you do that instead of just being told derivative of x squared is 2x, right? You go through that because it helps you understand what it means when you say the derivative of x squared is 2x. It helps you understand this is an incremental rate of change. And so this is why we're doing this in C and then moving into Java, so that, Java, you want a linked list, you just say, here's an object of type linked list. But to really know what that means and how to use it, it helps to understand how a linked list works. And so that's what we're getting here by doing this in C. Or if we were to do it in some other lower level language.
It's really starting to make the OO concepts way clearer for me.
Awesome.
As we go along and do this.
That's very cool. Yeah, and I know cases where students are sort of, introduced to object-oriented programming first, and it can, even though it's a great convenience and it makes coding easier for experienced coders, it can be like really confusing if that's your introduction, because there's so much stuff going on. When you make a string, there's so much happening beyond, just declaring a variable. So we will get to some really fun versions of this in 223, but I think it's pretty fun doing it barehanded like this also. All right, so pseudocode for chaining is I don't even know if we need to write any of it out, right? But we can start it. So, put key, comma, data. All right, so location equals hash of key. So we don't have a probe value here. This is just a hash function, takes a key, gives you an index. So if we look at hash bracket location, that should be a sentinel node. And if it's done in the style of PA1, we could simply say add hash bracket location, comma, data. There's our put function. Now the add function from PA1 was made for integers, and it was adding stuff to keep it in sorted order. We don't need to do that. So the fastest way to add something to a linked list is to put it right after the sentinel. So this would be like our push function from PA2. And then if you want to fetch, right, find out where in the array the sentinel is for the list that should contain your data, and then I don't remember what our PA1 functions look like anymore. Well, we didn't have a fetch. We had a search. So let's search for hash bracket location, right? So the index of the sentinel node. Let's look at that sentinel node, and let's look for the key. And if that key was found in our linked list, this would return a 1. But our list is a little different. Our list looks like this, right? So our my nodes would be a little different. Let me just call it a node. So it would have a key, it would have a data, and it would have a next field that points to the next node. And so usually with a hash table, we're interested in the keys. We store things based on key. We retrieve things based on key. We delete things based on key. The data just kind of comes along for the ride. It's what we can consider a payload. So if we thought of it as a linked list in the PA1 sense, the two fields would be, the data field would be the key, the next field would be the next. But we would also throw into each node the data associated with that key. So our add function would need to know, the key and the data, both of which we want to store inside this structure node. And our search function in PA1 was just a binary. Is the data in there or not? But here we would want something like, maybe a get that takes a sentinel node and a key, and if it finds it, returns the data piece associated with it. So if we search for a particular key, we'll start from the sentinel, we'll check the key. When we find the key, we'll return the data piece. And so we'll do a get on this and then just return data. And delete would be like put. We'd find the location of the sentinel node. Oh, thank you. We'd pass that as the first argument to the delete function, and we'd pass the key as the second argument. And someone just mentioned in chat that their first real language was C#, and they kind of got overwhelmed by all of the machinery and mechanics of that language. And I can relate to that. Whoa, freaky shadows. Alright, so questions about this hash stuff. It's a first foray into it, and we'll talk more about it with respect to PA3. And I hope to talk about PA3 Monday and Tuesday next week. So we'll get into that. So good so far?
So far, so good.
Okay. So let me switch gears here for a few minutes and go back to linked lists. Forget about hash tables for now. Let's go back to our first week's topic of linked lists, and I want to look at a few more aspects of linked lists. The first one being a doubly linked list, and this has come up in conversation during class before. But, you know, our usual linked list looks like this. And maybe our sentinel node, you know, points to our 10 and so on. And it's a simple structure, but it is a little complicated to use for some things. For example, trying to insert in order. We can't just search until we find a node before which we want to insert. We need to know what the previous node is. So we have this whole previous current pair that we use. So one modification we can make is we can enhance our structure to have three fields. Make it doubly linked. So we have a data node, we have a next node, and we have a prior node. And so this would point back to the prior node, and this would point back to the prior node, and this would point back to maybe the prior node. And so we have a pair of pointers in each node. And now if we want to insert, you know, a 15, we can start at the sentinel, we can follow the forward pointers until we get to a node that's bigger than 15. That's this node right here. And we can just call that current. And we don't need to have remembered what the prior node was. We can get to it by looking at current, arrow, prior. That points to the node right before. And so if we want to sandwich a new node in with a 15, well, we got to do a little more work now, but it's certainly doable. So if we're at current, we would want to do something like current arrow prior, which is this node, arrow next equals new. So that would start from current, it would follow the prior field to find this node's address, it would look at its next field, and it would change that to point to new. And we could do new prior equals current prior. So this would point to whatever current's prior was pointing to, which is this node right here. So we've got the prior node's next field set up. We don't need to change the prior node's prior field. We have the new node's prior field. We need the new node to point to current. So we could say new next equals current. And that sets up this pointer. And then we need to change current prior and set that equal to new. So this comes back here. And if you do this right, and I can't guarantee I did it right, we can follow the links forward. Sentinel points to 10. 10 will point to 15. 15 will point to 20. 20 points to 30, and so on. 30 points backwards to 20. 20 points backwards to 15. 15 points backwards to 10, and so on.
Funny, my only problems with navigating through the linked lists have been making sure that everything's done in an order that it's not overwriting itself, or like overwriting the previous with the new, and then, you know, and then trying to set the new to the previous.
So if I had changed current prior first, then this instruction doesn't make sense anymore. So that's definitely a challenge. Let me suggest a way to totally avoid that. Right? Use temporary variables. So I've got a new variable right here called new. I'm going to make a variable before equals current arrow prior. So this block's going to be called before. And maybe I'll rename this after equals current, so I'll name this after. And here's new. And now I can write my statements in any order I want, because I'm not going to change what before and after are. So now my statements will look like before, next, equals new, new prior, equals before, new next, equals after, and after prior, equals new. And I can do those in any order I want. Because what I'm doing is I'm saving the information from these nodes in local variables. So it doesn't matter when I change current arrow prior, right? I've already saved the value I actually want in this variable before. And if I change, you know, current arrow prior somewhere else, that's okay. And this is going to help us a lot.
I was muted.
Say again?
I said, sorry, I was talking, I was muted.
Oh, okay.
Responding to that. So it's kind of like what we did with the regular linked list, where we did just current and previous.
Yep.
Okay.
And this is key, right? When we start working with binary trees, and probably around week 7 or 8, we'll start doing what we call balancing AVL trees. We're going to get into some fairly complex manipulations of data we've allocated in memory. And if we do something like this, if we just, you know, use lots of local variables to point to the nodes that we're interested in, our life will be a lot simpler than if we try to you know, do everything by referencing relative to one node or two nodes. So this is always an option, and I think it's a good one, especially the first times that you're working through an algorithm and trying to figure out how to code it. Don't give yourself extra debugging challenges by, you know, possibly, you know, making typos or doing things in an order that changes the intent and so on. Give yourself lots of variables to work with. And, you know, keep tying it back to pictures. If I didn't have a picture, I would have a really hard time writing this, you know, scribbling this algorithm down on paper. Having the picture lets me more clearly, you know, say, okay, here's where I'm going to go from there, and so on and so forth. All right, so we'll play around with this more on Thursday, and then we'll start talking about something else. All right, have a good one. I will see everybody next time.
Thank you.
Cool, thanks a lot.
Thank you.